Okay, in most of this chapter we've been talking about proton NMR, but in organic chemistry, another useful technique is carbon-13 NMR. Now, because hydrogen 1 is by far the most abundant isotope of hydrogen, proton NMR signals are generally very strong. However, carbon-12 is not usable in NMR because we have even numbers of protons and neutrons. So the isotope of carbon that we can use in NMR is carbon-13, but carbon-13 only accounts for about 1% of all carbon atoms in nature. So we either need a very sensitive instrument or we need a concentrated NMR sample in order to do carbon-13 NMR. In proton NMR, we looked at a lot of things that influence the spectra. We looked at the number of signals, the chemical shift, the splitting, and the integration. In the case of carbon-13 NMR, we're not going to be able to use integration to tell us how many carbon atoms are contributing to that signal. That being said, a lot of what we've already talked about for proton NMR holds true for carbon-13 NMR. The number of signals tells us how many unique carbon atoms there are, right? The ones that are interchangeable by symmetry are going to contribute to the same signal. And then the chemical shift works very similarly to the way it does in proton NMR. If we have carbons attached to electronegative atoms, or if they're part of conjugated pi bonds, then they're going to tend to be downfield. And then sp3 hybridized carbons tend to be fairly far upfield. And you'll get this table in the data cards, just like the other tables that we have for proton NMR that you can use as reference. One of the big differences between carbon-13 NMR and proton NMR is what the splitting tells us. So in proton NMR, the splitting tells us about how many hydrogens there are on adjacent carbon atoms. In carbon-13 NMR, it tells us how many hydrogens are attached to that specific carbon. But the N+1 rule still holds true. So let's look at a quick example. Generally, the data you're going to be given doesn't have the carbon-13 NMR spectra, or at least what you're going to be getting in lab. I think the ones in the book, you'll actually be getting the spectra. What you're going to get in lab is typically just going to be a list of the chemical shifts and then also what the splittings are. Now, one difference, the carbon-13 data that we're going to be getting in lab is what's called proton-coupled carbon-13 NMR, and so in that case we do get splittings. If you notice the discussion in the book, they don't have splittings in the carbon-13 NMR spectrum, so we're going to have a little bit of extra data than the spectra that you see in the book. And so when we look at these chemical shifts, right, we can see, right, this carbon that's attached to two very electronegative oxygen atoms, right, it's shifted fairly far downfield, right, and then just like we'd expect in the proton NMR, right, as we get further away from that carboxylic acid group, the chemical shifts decrease. And if we were going to predict what the splitting would be for each one of our carbons, in this case we don't have any identical carbons, all of the carbons are unique, and the splittings that we'd expect, so this carbon is a CH3, so N+1, we would expect a quartet. Right, then for a CH2, we'd expect a triplet. And again, these CH2s, we'd expect to see triplets. And then because this carbon doesn't have any hydrogens, we'd expect it to be a singlet.